Kinematics is a very important area in the engineering block of robotics. Kinematics, in fact, is a subfield of physics, a subfield that deals with movement without regard to forces. And kinematics speaks about things like positions, trajectories, speeds, acceleration. Well, it's not really a common classification, but I suggest to divide the field of kinematics in, let's say, two subfields. And that division is based on the different robotic shapes I suggested in a previous video. The first subfield is devoted to what I call link-based robots, and it refers especially to the kinematics of fixed industrial manipulators. But it also can be applied, for example, to humanoid robots. The other subfield has to do with what I call box-like robots, and it's more preoccupied about movement, about trajectories, about navigation. We'll speak about navigation in another video, so we'll remain now in the kinematics of link-based systems. And there's a distinction between what is called forward kinematics and inverse kinematics. And the distinction depends on what you have and what you're trying to get. In forward kinematics, what you have is the commands you're giving to the robot, and what you want to know is the final position after applying those commands. In inverse kinematics, you know the target position you want to arrive, and what you're looking for are the commands you need to achieve that final position, let's say. There's a lot of mathematical apparatus behind kinematics. And it turns out that most of the calculus is based on linear algebra. You use vectors to express positions, but you need to define what are called frameworks of reference to express those positions. A framework of reference is nothing more than the typical X, Y, Z orthogonal axis you're surely used to. And you define one, let's say, basic framework of reference, usually where the robot is grounded, especially in industrial manipulators, but you also need another framework or reference that you position, for example, in what is the shoulder, the elbow, or the wrist of the robot. You express the positions using vectors defined in that space defined by the frameworks or reference, and movements, let's say translations, rotations, are the result of applying transformation matrices to vectors. Well, there's a lot of complexity here, and I won't deal with it. Kinematics is a very important field, and so in classical books about robotics, for example, this one, there's usually one chapter or two or three speaking about kinematics, but you can find it also in books like this one about humanoid robots. Well, I will not continue explaining complex things, but you get the idea, and I encourage you, if you are really interested, to read these kinds of books I've showed to you.